Hello everybody, it's Mrs. Walsh and this is our video lesson on congruent figures. I think a lot of this is going to be review for you. I think it's a good lesson to do via video. Just make sure that you're really comfortable with all these concepts and that you're taking good notes. Congruent polygons are polygons that have congruent corresponding parts, okay? So that means every side, every angle, they're congruent. But you must match the sides and the angles, and when you're discussing polygons and calling them congruent, this is where kids definitely get in trouble, is you've got to think about listing the corresponding vertices in the same order. So if we look at these two polygons, and I'm talking about polygon K, J, I, H, and I want to call it congruent to another polygon. I can't just start listing this any which way I want. We've got to decide which parts correspond with which parts. And you can see, or if you kind of have to flip this and rotate it, but this one corresponds with this angle, and this angle corresponds with this angle. So you can see how I kind of flipped it over, and then this one actually corresponds with this one. And then H and L correspond, and you have to kind of just visualize how you would flip this and rotate it. So if I'm going to call these two figures congruent, I have to list the corresponding vertices in the same order. K corresponds with O, so I have to write that first. J corresponds with N, so I need to write that second. I corresponds with M, so I need to write that third. And then H corresponds with L, so I need to write that fourth, because K has to go with O, J has to go with N, I has to go with M, and H has to go with L, and that's very important. If you don't write it that way, then it's not a true statement. Okay, so now if we're trying to look at these triangles and ask if they're congruent, for something to be congruent, all their corresponding parts need to match up. And so if I have triangle ABC, and let's look at that, I can see that A has this one little dash and that one little dash over there, and B has 2, and D has 2. What about C? Do you notice anything about these angles? I hope that you notice their vertical angles, so I can call them congruent. Is a side length of 4 congruent to a side length of 4? Well, it sure is. Is a side length of 6 congruent to a side length of 6? Well, it sure is. So now, do I have 3 corresponding angles that are congruent and 3 corresponding sides that are congruent? I do. So I can make my congruent statement that triangle ABC, and let's be careful of the order here, is congruent to triangle. I need first just the 1, now the 2, and now the 3. So if you don't write it this way, it wouldn't be right, because it's A, B, C. A corresponds with E, B corresponds with D, and of course C, those are vertical angles. Now, there's a theorem, the third angles theorem. If two angles of one triangle are congruent to 2 angles of another triangle, then the third angles are congruent. Well, that should be logical to us all, because since we learned the triangle angle sum theorem, if these two are congruent to each other, this one must be congruent. It must be, because they all must add up to 180. So that's what the third angles theorem is. If we were going to prove it, and I'll do it in a little less formal fashion, I would know that angle A is congruent to angle D, and angle B is congruent to angle E. And I would know that the measure of angle A plus the measure of angle B plus the measure of angle C must be equal to 180. And that's just the triangle angle sum theorem. And I would also be able to state that the measure of angle D plus the measure of angle E plus the measure of angle F is equal to 180. Once again, this is just the triangle angle sum theorem. And up here, I could make corresponding statements that the measure of angle A plus the measure of is equal to the measure of angle D. That's the definition of congruence. And the measure of angle B is equal to the measure of angle E. Once again, the definition of congruence. Now I have some interesting things I can do, right? These are both equal to 180. I can set them equal to each other using the transitive property. So the measure of angle A plus the measure of angle B plus the measure of angle C is equal to the measure of angle D plus the measure of angle E plus the measure of angle F. But we have a couple of substitutions we can make here. And I'll just substitute A for D. So I'm going to rewrite this statement. B plus measure of angle C is equal to the measure of angle A via substitution plus the measure of angle B via substitution plus the measure of angle F. And you can see here, if I use the substitution property of equality, the subtraction property of equality, if I subtract measure of angle A from both sides and measure of angle B from both sides, I am left with the measure of angle C equal to the measure of angle F. And if that's true, then I've just proven that angle C is congruent to angle F by the definition of congruence. All right, so here's a proof for you to try. I'm not going to do it on this slide, but once again, it's an opportunity for extra credit. If you're given that A is congruent to D, that AE is congruent to DC, that EB is congruent to CB, and BA is congruent to BD, I want you to prove that those two triangles are congruent. So try to work that out and bring it in. Tomorrow we'll talk about it. All right, this part is really a review. I just want to make sure we're all on the same page in terms of our vocabulary with triangles and angles. This is stuff we should have learned perhaps in elementary school. Okay, so triangles. What is the definition of triangle? It's a figure formed by three segments joining three non-collinear points, because we know the problem is if they were collinear, the 3 points, it would just make a line, right? So anytime we have three non-collinear points and we connect them with segments, we have a triangle. We name triangles by these 3 points. So we would call this triangle, triangle QRS. Now, each of the 3 points has an official vocabulary name called a vertice. And adjacent sides, these are all vertices. And adjacent sides are two sides that share a common vertex. So in this case, we could say that AB and AC are adjacent because they share the vertex A. And the third side is opposite the given vertex. So if we're ever trying to refer to this side, BC, we could say it's opposite vertex A. Now, there are lots of ways we have learned to classify triangles, both by angle, in which case we have acute triangles, and I hope we all know that acute triangles are triangles in which no angle measures 90 degrees or more. So I guess a better way of saying this would be all angles are less than 90 degrees. Okay, the next one, obtuse angles. One angle is greater than 90 degrees. That's the definition for an obtuse angle. And then for a right angle, what do you think it is? I hope you know it's one angle is equal to 90 degrees. Now, equiangular is another way I don't know if you've heard of to classify triangles, but that means all the angles are equal. And for that to be the case, what must they all be? 60 degrees. And this would also then be an equilateral triangle. But that, when we say equilateral, we're defining by sides. So if we look at definition by sides, the first one is scalene. And no sides have the same measure in a scalene triangle. They're all different. No sides have the same measure. Now, in an isosceles, and I want you to be careful because I think this is one of these you can get tripped up on. The official definition is at least two sides are the same. At least two sides are the same. That means all three could be the same and you could still call it isosceles. But if all three are the same, we have another name for that, and it's equilateral. So the question I would have you, these are all sides are congruent. So if I were to ask you, are all equilateral triangles isosceles, I hope you would say no. And if I were to ask you, if all equilateral triangles are isosceles, I hope you would say yes. And if I were to ask you, are all isosceles equilateral triangles, I would ask you to say no. So if the question were phrased as an always, sometimes, never, are isosceles triangles equilateral triangles? Sometimes. Are equilateral triangles isosceles triangles? Always. Are scalene triangles isosceles triangles? Never. Hope all that made sense. Okay. Now, just so we know the names for parts of a right triangle, when we have a right triangle, we call the two sides that are adjacent to the right angle legs. And we call the side opposite the right angle the hypotenuse. In an isosceles triangle, we actually call the two congruent sides legs, and the opposite, the remaining side, the base. How can ABC be right and isosceles? Well, if this were 90 and this were 45 and this were 45, these two side lengths could be the same, and it could still be a right triangle and be isosceles, because right is referring to angles and isosceles is referring to side lengths. So they are not mutually exclusive. You can be a right triangle by your angle measures and isosceles by your side lengths. Okay, and just so we're all clear, when we're discussing interior angles, we're talking about these angles that are inside the triangle. When we're talking about exterior angles, and I hope we're all familiar with this because of the theorem we learned in the last unit, an exterior angle is formed by extending the side of a triangle, and if you extend it, it's that extended side with the opposite side. So there's an exterior, here's an exterior, here's an exterior. If I extended this way, this would be exterior. If I extended it this way, this would be exterior. This one's exterior. So those are all exterior angles. Okay, so that's it. This was mostly a review video. Hopefully it all made sense, and I'll see you guys tomorrow.